In hot gas filtration, operators face the unique challenge of maintaining purity and efficiency under extreme temperatures. Conventional filter media often struggle to balance fine particle capture with structural integrity when exposed to thermal cycling and corrosive gas streams. This can lead to early system failures, rising emissions, and expensive standstills. For facilities under strict environmental regulations, even minor inefficiencies can compromise compliance and production targets. Woven wire mesh has emerged as one of the preferred filtration mediums of these demanding conditions. Its customizable architecture allows engineers to fine-tune pore size, porosity, and laminate thickness to achieve precise filtration performance while withstanding temperatures up to 600 degrees Celsius or more. When paired with the right alloy and weave style, wire mesh delivers exceptional mechanical strength, corrosion resistance, and regenerabilities, which are all qualities that ceramic or fabric filters often cannot match. Hot gas filtration is about more than just capturing particles. It's about doing so under punishing conditions, where temperatures can soar past 600 degrees Celsius and corrosive compounds attack every surface. At these extremes, the mesh must maintain structural integrity while delivering consistent filtration performance. This is why specifications such as pore distribution, permeability, total porosity, and laminate thickness are critical. These parameters dictate how the filter handles pressure drop, how quickly a filter cake forms, and how effectively the system recovers after back pulsing cleaning cycles. A poorly specified mesh can lead to unstable pressure drop, frequent cleaning cycles, and even catastrophic failure. The mean pore size and its distribution determines the filter's cut point, which is the smallest particle it can reliably capture. Narrowing the distribution improves fine particulate capture, but raises pressure drop and can slow cake formation. Conversely, high porosity and permeability reduces energy consumption and stabilizes pressure drop. But if they're too high, emissions may spike before a cake forms. Engineers often use a graded laminate design, a fine surface layer for precision capture, supported by open layers for strength and flow. This approach balances emissions control with energy efficiency, a best practice confirmed by recent industry standards. Specifying burst strength, flexural stiffness, and creep resistance at room temperature is a common mistake. These properties must be evaluated at the actual operating temperature because metals behave differently under thermal stress. At 600 degrees Celsius, even stainless steel can experience creep, while alloys like Inconel or Hastelloy maintain strength and resist oxidation. ISO 4783 and ASTM E2016 standards emphasize dimensional stability and mechanical integrity for woven wire mesh that can be applied in high temperature environments. Without these considerations, filters risk deformation during thermal cycling or failure under back pulse loads. And material chemistry is as important as pore geometry. Gas streams often contain halides, sulfur compounds, or acidic dew points that can corrode standard stainless steels. These systems insulated above the acid dew point, 316L stainless steel may suffice, but harsher conditions do justify high nickel alloys such as Inconel or Hastelloy. These alloys form protective oxide layers that resist scaling and spillation during thermal cycling, helping to extend the life of the filter and reduce necessary downtime. Selecting the right alloy upfront prevents costly retrofits and ensures compliance with emission standards over the long term. Designing wire mesh for hot gas filtration is not just about achieving the lowest emissions, but doing so without inflating operational costs. Overspecifying mesh can lead to unnecessary pressure drop, higher fan power consumption, and increased pulse frequency, all of which drive up energy costs. Conversely, cutting corners on mesh quality can compromise emissions and shorten filter life. The key is value engineering, applying precision only where it delivers measurable benefits, while standardizing where possible to reduce cost and lead times. The most effective way to optimize mesh design is to begin with the emissions limit and particle size distribution. This allows engineers to select the coarsest surface layer that will reliably meet the emissions target once a thin filter cake forms. Using a graded laminate, which is one fine layer for the cut point over one or two open support layers, minimizes pressure drop and pulse frequency while maintaining structural integrity. This approach is widely recognized as best practice for balancing performance and energy efficiency in high temperature filtration systems. But not every application requires custom mesh counts or exotic alloys. Standardizing on widely produced mesh sizes reduces procurement costs and shortens lead times. Similarly, sizing laminate thickness is critical. Excess metal adds weight and raises pressure drop without improving emissions or durability. Industry guidelines emphasizes avoiding overbuilding filters, as this results in higher operating costs without any real tangible performance gains. Material choice is another area where cost and performance intersect. While high nickel alloys like Inconel or Hastelloy offer superior oxidization and corrosion resistance, they may not be necessary if the system operates above the dew point and gas chemistry is controlled. In such cases, 316L stainless steel often provides adequate protection at a fraction of the cost. Advanced standards confirm that matching alloy grades to process conditions, while not defaulting to premium materials, materials can significantly reduce cost of ownership without sacrificing reliability. The weave pattern of woven wire mesh is not just an aesthetic choice. It directly influences filtration performance, cleanability, and durability. Plain and twilled weaves offer robust mechanical stability and are more forgiving under thermal shock and frequent pulsing, making them ideal for systems with aggressive cleaning cycles. Dutch and reverse Dutch weaves, on the other hand, deliver tighter effective pore sizes at a given thickness, improving fine particle capture. However, these tighter weaves can retain sticky fines, which may complicate cake release during back pulsing. Selecting the right weave style ensures a balance between filtration precision and operational reliability. Compressing the mesh under rolls, also known as calendaring, improves demolding and enhances cake release. It also tightens the cut point by reducing pore size variability, which can improve emissions control. However, over-calendaring can collapse geometry pores and reduce permeability, leading to higher pressure drop and energy costs. Industry best practices recommend moderate calendaring to achieve a uniform surface without sacrificing flow characteristics. For multi-layer laminates, sinter bonding is essential. This process fuses layers together under pressure at high temperatures, creating a rigid structure that resists delamination under thermal cycling and back pulse loads. Sintered laminates maintain dimensional stability and allow engineers to combine different mesh counts, which are generally fine layers for filtration and open layers for support, without compromising strength. This technique is widely adopted in high temperature filtration systems for its ability to extend filter life and maintain consistent performance. Post-processing choices must align with operational properties. For example, a system dealing with sticky particulates may benefit from lighter calendaring and a plain weave to improve cake release, while a system targeting ultrafine emissions might require a tighter Dutch weave and aggressive calendaring for precision. Combining these techniques with proper alloy selection and laminate design ensures that the filter meets emissions targets without sacrificing cleanability or energy efficiency. This holistic approach is now considered a cornerstone of advanced hot gas filtration designs. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things W.S. Tyler. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.